get started? So we have a test next week, don't we? That's ridiculous, having a test 3 weeks later, right? Doesn't it feel like we just got through with the one? Yeah, well, it's okay. It's okay. So usually the second midterm is the one that is so stressful because there's so much material. So it's going to be a little less material. So that's good. That's good for you. Are there any questions before we get started? Yes. Say that one more time.
When you superimpose
yeah.
do you go like
So he's asking about superimposing a molecule, and if you did it with molecules, you could do whatever you need to. You can rotate, you can whatever, flip, whatever, just so that you see that you can put one right on top of the other and all the bonds match. So there's no rules for superimposing. When we do the turning the page, like when I flip it like that, that's one thing that many people can do in their head, and so I do it that way, but not everybody can do that in their head. But it doesn't mean that you have to do it that way. You can do it any way you want. Okay, so we're going to finish chapter 5 tomorrow. Not tomorrow, on Friday. So certainly all of chapter 5 will be on the midterm, and some of chapter 6. And the good news is chapter 6 is not super difficult, and it's going to feel like some of it's going to be review from GChem. Okay, so hopefully that won't be too bad. All right, so we're talking about enantiomers last time. So if we have a pair of enantiomers, we have two molecules that are chiral that are mirror images of each other, and they are not superimposable. So this was on the previous page. So it turns out that enantiomers have identical boiling points, melting points, solubility, index of refraction, IR, NMR, and achiral solvent, etc. So the thing that's different about enantiomers is when they interact with other chiral substances, there will be differences. And when they interact with plane polarized light. So enantiomers rotate the plane of polarized light by exactly the same amount, but in the opposite direction. And what we use to measure this is a polarimeter. And a polarimeter will give us a measurement of the optical rotation. The specific rotation of a compound is calculated using the following formula. So this is a formula that you're going to need. This is, and the way that I am with formulas is I don't want you to memorize formulas. So if I have you use this formula on the test, which I almost certainly will, I will provide it for you, so you don't need to memorize. All right, so this is specific rotation, and this is a specific rotation at a certain temperature using the line from the D line visible spectrum of sodium, the wavelength of 589. So the fact that we have this in brackets and the T and the D means that is at a specific circumstance, at a specific rotation, at a specific time using the D line of the visible spectrum of sodium. So this is a specific rotation, not to be confused with the measured angle of rotation. So this is the measurement from the polarimeter. So this would be the number that you would get directly off the polarimeter. And what we're trying to do is we're trying to correct for every possible variation so that if somebody in Germany right now were to measure the optical rotation of a compound that you've measured, they should get the exact specific rotation that you did. And so the rotation is actually going to vary depending on your concentration, what solvent you use. And so if we just left it the measurement from the instrument, we would get all sorts of numbers. So we're correcting for all of those things. So we're going to be correcting for the concentration of the sample in grams per milliliter, and we're going to be correcting for the length of the sample tube. So there are different lengths of sample tubes, although 1 decimeter is really common. This is the most common length. So the light is going to travel through the substance, and so the length of the tube that it's in and the concentration is going to make a difference. So we're going to be using this this formula to do calculations. There's no obvious correlation between the configuration of enantiomers and the direction in which they rotate plane polarized light. So sign and magnitude. Is an experimental measurement. So I can't look at a compound and tell you whether it's going to have a positive or a negative rotation. Can't possibly do that, would not be able to do that. And nobody could do that. It would be something where you would put it in a polarimeter and you'd measure it, and that's the only way to know. A sample of pure chiral compound, uncontaminated by its enantiomer, is said to be enantiomerically pure or optically pure. Those are the two terms we use for this. An equimolar mixture of enantiomers is called a racemic mixture. And a racemic mixture has an optical rotation of 0. So let's say, for example, our +2 bromobutane example that we were looking at previously. We have +2 bromobutane. Has a specific rotation. I'm just going to put it in brackets. I'm not going to draw the little t and the d. I'm just going to put it in brackets. And has optical rotation of +23.1 degrees. So the measurement is in degrees. The other enantiomer of 2-bromobutane has a specific rotation of -23.1, and that will always be the same. A pair of enantiomers will have the opposite rotation. So if you have a racemic mixture, a racemic mixture means 50% one, 50% the other. 50% of the plus isomer and 50% of the minus an isomer. So if +23.1 degrees, and we have -23.1 degrees, and it's just like adding together positive and negative numbers, it's going to add up to 0. Optical rotation of racemic mixture will be 0 degrees. All right, so if you don't have 50-50, if you have 60-40, then you will have a rotation. So if you have, say, for example, you had 60% of the plus enantiomer and 60% of the and 40% of the other, then you would have a positive rotation overall. It would be smaller than 23.1, but it would be positive. So this does not mean that a racemic mixture is achiral. It just means that the two values are canceling each other out because you have a 50-50 mixture. So chirality is a property of individual molecules or objects. A chiral molecule has this property whether it's mixed with its enantiomer or not. Optical activity is a physical property. Chirality is a structural attribute. Okay, so just because the optical rotation, if you measure something and the optical rotation is 0, that means that you either have something that's achiral or you have a racemic mixture. Okay, so you don't know which is which. All right, so that leads us into enantiomeric excess. A pure sample of single enantiomer is said to be enantiomerically pure or have enantiomeric excess of 100%. If the sample is contaminated with the other enantiomer, the mixture will show an optical rotation corresponding to the percent of the species present in excess. So the percent EE will be less than 100%. All right, so on percent EE, we can also call this or optical purity. All right, so let's do some calculations here. A sample of 2-bromobutane has a specific rotation of plus 11.55. The specific rotation of plus 2-bromobutane at 22 degrees centigrade is plus 23.1. What is the enantiomeric excess of plus 2-bromobutane in this sample? All right, so we're going to use this formula. Percent EE equals optical purity equals plus 11.55 divided by plus 23.1 times 100%, and that's equal to 50% EE. So this would be the enantiomeric excess of plus 2-bromobutane. So 50% EE does not mean that you have 50% of one and 50% of the other. It means that you have one of the enantiomers is 50% in excess of the other. It's not a 50-50 mixture, because if it was a 50-50 mixture, then the optical rotation would be 0, right? Okay, so yeah, question.
So is that like you have 1 unit of the 2-bromobutane and you have 1.5 units of the plus 2?
Yeah, and that's what we're going to do in the next one here. Example 2, what's the stereoisomeric composition of a mixture of 2 bromobutanes with 50% EE of plus 2-bromobutane? All right, so if we have a mixture with 50% EE, we have 50% plus 2-bromobutane and 50% plus minus 2-bromobutane. So that means that we have 50% of a racemic mixture and then 50% of the plus in excess. So you see what the percent EE is. It's the percent in excess. So this means that for this we have 25% plus 2-bromobutane and 25% minus 2-bromobutane. So if we want the stereoisomeric composition, that's the percent of each enantiomer. So the stereoisomeric composition is 50% plus 25% plus isomer. So we have 75% of the plus 2-bromobutane. And 25% minus 2-bromobutane. So the polarimeter can only see what's in excess, okay? So if it's only going to see this, then that means that this it doesn't see because the two are canceling each other out. Questions on that? Anybody? There are some, I opened up sapling last night. Please do not wait till the last minute for the chapter 5 sapling, because there's some calculations similar to this, but a little bit more challenging that test to see what if you really know what we're talking about. And you will need to bring a non-graphing calculator to the midterm. This, I think, will be the only exam where you will be allowed to bring a calculator. Maybe. But definitely you want to bring a non-graphing calculator. So do not bring in a graphing calculator and take it up here and ask me to clear the memory. We don't have time to do that when we're giving a test. This test that's coming up is the test that everybody needs the whole amount of time. I will see very few people leaving early because stereochemistry, it's tricky, and it's especially tricky when you're in a nervous test-taking situation. So I don't have time to clear people's memories, so please, I mean, they're less than $10. You can even get it at the bookstore, just the regular non-graphing kind. All right, questions so far, anybody? All right. So what's going to happen over the weekend is I'm going to decide on Friday how far into Chapter 6 we will go for the midterm. And then I will open up Sapling for Chapter 6, and I will send an email to tell you which problems would be relevant to the material on midterm 2. But the Chapter 6 Sapling will not be due till after the midterm. Okay? Everybody clear on that? Let's talk about configuration, representation, and nomenclature of stereoisomers. So if we have a sample of -2 bromobutane and a sample of +2 bromobutane, these samples have the opposite relative configuration. The optical rotation tells us nothing about the absolute configuration, which is the actual orientation in space of the groups around a stereocenter. So I can't look at +2 bromobutane and say, oh, that's plus. That means, oh, this is, and then be able to draw it, exactly what it looks like. Okay, I don't know the orientation of the groups by measuring optical rotation. I know if I have a sample of the plus, and I know if I have a sample of the minus, and I know if I have mixtures of the two in different combinations, but I don't know what they actually look like to be able to, for somebody to be able to draw what it is. Nobody does. Okay, so this is here. It turns out that -2 bromobutane looks like this. This is the orientation of the groups. This is the absolute configuration of -2 bromobutane. The optical rotation is that's a measured optical rotation is minus. Does not tell us anything about the structure. So that's a measured optical rotation, and this is measured. How do we know the absolute configuration? Pretty tricky. There's different ways to figure this out. How do we know? Different ways. A couple that I'll just mention here. A crystal structure, if it's a solid, you could be able to see exactly the orientation of the atoms. So crystal structure. If solid, there's other techniques like anomalous dispersion. And even newer techniques that we're not going to list here, but you would have to use something else. The point of this being you have to use something else to figure out what the absolute configuration is. A couple things, they both start with C. Configuration and conformation are not the same thing. Configuration of a compound is unchanged unless at least one bond at the stereocenter is broken. Okay, so we have to if we want to change from one enantiomer to the other, we have to actually physically remove 2 bonds, switch them. So with a model, you have to physically break 2 bonds. And then change their location. So that's the absolute configuration. The conformation of a molecule changes continuously at room temperature as a result of rotation about single bonds and flipping of rings and all the things we learned about in Chapter 4. Okay, so that's a completely different thing. So a stereoisomer has a single configuration but may exist in a number of conformations, and it certainly does have many, many, many conformations. So if we look at this compound right here, we have one stereocenter, one stereocenter, or chiral center, or chirality center. And then as I was looking through Sapling last night, they use another term that I did not mention already, and that's an asymmetric carbon. So all of those are terms for the same thing. And we use a little asterisk to signify that that is our chiral center, stereocenter. I don't usually use asymmetric carbon, and I don't usually use chirality center, but you will see those terms. So this is a single configuration. So single configuration. But we have the same molecule. We have many conformations of the same stereoisomer. So each one of these molecules has that single stereocenter, but we have many, many, many conformations. We can flip, we can go, do all sorts of things here. All right, so we need a way to specify. I mean, again, we've got our friend in Germany, and we're talking molecules, and we have -2 bromobutane, and we want to convey what that means. So, you know, a little hard to describe if you were going to just describe it. Okay, well, you've got the carbon here, and then draw the methyl straight up, and the ethyl to the left, and then, you know, hydrogen on the you know, it's not a very easy way to convey. You could kind of describe it, but it would be a long description, kind of like giving somebody directions to your house or something like that. So we have a way of signifying absolute configuration. They're called the Kohn-Ingold-Prelog rules. And we're going to signify every stereocenter by either R for rectus or right-handed, and that's equivalent to clockwise, and S from the Latin sinister or left-handed counterclockwise, and that just comes from back in the old days when they thought that left-handedness was a mark of the devil, right? And they tried to make people not write with their left hand. They had to write with their right hand. And so that's where that terminology comes from, kind of a little bit unfortunate here. But that's counterclockwise. So R is clockwise, and S is counterclockwise. I have 3 left-handed people in my family, so it's not, you know, certainly nothing sinister about it. All right. So what we're going to do is we're going to assign priorities, 1, 2, 3, or 4 to the atoms directly bonded to the stereocenter. Okay? Higher atomic numbers receive higher priority. So chlorine will be higher than oxygen, which will be higher than nitrogen, higher than carbon, carbon than hydrogen. Isotopes, higher atomic mass takes priority. So tritium would have a higher priority than a deuterium, which should have higher priority than a hydrogen. In case of ties, so if the 2 atoms bonded to the stereocenter are the same, then we move out 1 atom at a time until we see a difference. Okay, so we start here with an ethyl group, and basically we're just talking about this group being bonded to the stereocenter. So we have a carbon, and here we have a carbon and 2 methyls, so that's going to have higher priority. Carbon with 3 methyls is going to have higher priority. And then if we move on and we have 1 chlorine, even though we only have 1 chlorine, we have 2 hydrogens, that's still higher priority. So you're going to follow the highest priority pathway here. So we have carbon-carbon, 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 carbon-chlorine. Carbon-chlorine is going to have higher priority. Okay, yeah?
Why does carbon-chlorine?
Because chlorine has a higher atomic number than carbon. So we're looking at the first point of difference here. All right, so the only reason we looked at the number of methyls here was because all those groups were the same, and that was kind of a dead end. So then we look at you know, how many carbons are attached to that carbon. And then we have 2 bromines here, so that's going to take higher priority. So let's mark this one, 1 chlorine, but still takes priority. Important, a priority decision is made at the first point of difference. So again, even though this carbon is attached to 3 carbons, this is higher priority because we're encountering a chlorine which has a higher atomic number. Double and triple bonds are treated as if each bond were a bond to a separate atom. So if we had something like this bonded to the stereocenter, I'm going to draw out the sigma bonds. We will sometimes need to do this. So in other words, if this carbon is bonded to, it has a double bond between these two carbons, then this carbon has one bond to the carbon and another bond to the carbon. So you can just draw it right here too. And that'll help you in some of these trickier ones where we have substituents like this. And triple bond, each carbon is essentially bonded to 3 carbons. So we have this sigma bond, and we have the 2 pi bonds. So you can just do it like this, and that's going to help you keep track of what's bonded to what. And carbon-nitrogen double bond here. Again, this carbon actually has 2 bonds to nitrogen, so here's the second bond. So I'm drawing the bonds, I'm drawing the pi bonds out from the atom that it's attached to, so I can kind of keep track of what's going on here. So that's going to help us determine which has a higher priority. So that's step 1. Step 2, we're going to view the chiral carbon with the lowest priority substituent away from the viewer. Trace a path from the first priority to the second to the third. So if we look at this, this molecule, for example, and what's going to be the highest priority? First atom carbon, hydrogen, oxygen takes priority. It's a higher atomic number, so this will be number 1. And ethyl is going to take priority over methyl, so this is number 2. And methyl here is going to be number 3. Hydrogen is number 4. I usually don't write a number for the lowest priority. I just direct it away. But you can. The number 4 is going to be away from the viewer. And then you're going to sight along that bond. So if you made this with your atoms, and I should have brought atoms, I didn't think about this, grab the lowest priority group and then just look at it like this. So you're looking at your molecule like this, your lowest priority is heading away from you. Okay? And if you were standing over here to the right, you kind of have to imagine yourself standing there. But if you trace the pathway 1, 2, 3, can you see that we are going clockwise? Okay, so arrows are clockwise. Therefore, the configuration is R. It is incredibly easy to make a mistake when you're assigning configuration, especially depending on where you start on the clock. Some people have to wear a watch, you know, and so if you wear a watch, that'll help. But it's really easy to make a mistake. So you just got to be careful when you're doing it, and just have a lot of practice so that it becomes easy to you. Questions on how I did that, anybody? All right, so this is going to be our configuration. Designation of a compound as RS has nothing to do with the sign of rotation. So because it's R does not mean it's positive rotation. We have things that are R that have negative. There's no correlation whatsoever. Absolutely no correlation whatsoever between the sign of the optical rotation. It's an experimentally determined value. So sign of optical rotation is an experimentally determined value. All right, so we don't have to draw these out or use a model every time. Some of you, so what we're also going to allow on midterm 2 is molecular models. You cannot put them in the case that they come in. Most of you have the green case. It has to be in a clear Ziploc bag. And you know why that is. We've had people in the past that have written cheat sheets inside their boxes. So it has to be in a clear Ziploc bag. So this is the exam where you're going to be allowed non-graphing calculator and models in a clear Ziploc bag. But what I urge you to do is to get enough practice that you don't really need your models to do this. Because the problem is that it takes time to do models. And it's going to slow you down in getting the test done. I remember as a student, and I brought my models in, and I'd be, and I'm kind of a nervous test taker, honestly. And I'd have my models, and I'm like, okay, the red's going to be methyl, the blue's going to be ethyl, green's going to be iodine, it's going to be whatever, and then I would make the model, and I'm like, okay, whoa, what was the green? The methyl was the, you know what I'm saying? It takes too much time, and it's way too easy to make mistakes. So I'm going to give you some tricks that will make it so that you don't have to actually make a model to determine configuration. Okay, so here's some different approaches for this particular one. Assign ROS configuration to the following amino acid alanine. And by the way, right, if you run out of time on the test, it's a 50-50 guess whether it's ROS, right?
Unless it says why.
Think of it. What?
Unless it says why.
Why? No, I wouldn't ask why. I wouldn't ask why for that. Okay, so priorities. Nitrogen is going to be first priority. This is carbon, 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 carbon. So since they're both carbon, we go to the next atom out. This is carbon, hydrogen. This is carbon, oxygen. So this is going to be number 2, and this is going to be number 3. So in case of a tie, we move out another atom. We keep moving out until we see a difference. Now this is a wonderful problem because the hydrogen is already drawn going back away from you. It's going into your page, and that's a beautiful thing because now we can easily trace this. Here, 1, 2, 3. So that is clockwise. Therefore, it's R alanine. All right, so what if the lowest priority substituent is not drawn going back? I'm going to give you some different approaches for this. Approach number 1, assign RS configuration with the lowest priority coming towards you, then switch. Okay, so here, lowest priority is forward. And I'm going to mark that because I don't want to forget. And so what I'm going to do is I'm going to prioritize here. The oxygen has higher priority here. And then ethyl takes higher priority over methyl. And then we have our methyl. And if we trace that pathway, that's clockwise. This is clockwise. But hydrogen is coming towards us. The lowest priority has to be back. Hydrogen is towards us. So it is it is S. So we just switch from one to the other. So that would be the S enantiomer of that compound. So that's approach number 1. If the lowest priority is in the plane of the paper, it is not in a dash or a reg, I urge you to use approach number 2 for that. Because it's really difficult. So in this example here, we have it drawn as a model so we can kind of imagine ourselves walking over to the side. But when it's dashes and wedges like this, a lot of people have trouble with that. So this would be easy. This would be difficult to assign configuration because I have to imagine myself walking over to this side of the molecule and looking at what I would see. And it's a lot harder to do. So a good way to handle that is approach number 2. Approach number 2, recognize that exchanging 2 groups at a stereocenter inverts the configuration of that carbon and converts it to a structure with only one stereocenter into its enantiomer. We already proved that last time, didn't we? We took an enantiomer, we took out 2 bonds and then we switched the 2 bonds and we made the other enantiomer, right? We did that on the Elmo. So that's one of the things that we can do. So we can exchange the hydrogen with the hydroxyl so that the hydrogen's going back. We term it RS configuration, and then we switch it back again because once we switch 2 groups, we've changed the configuration. So I'm going to exchange these 2 groups. If you do exchange 2 groups, I recommend that you write something to yourself to show you that you've exchanged 2 groups so that you remember to switch after you're done. All right, so I'm going to just actually redraw this. Hydrogen going back, hydroxyl coming forward. Ethyl still on top. If I switch 2 groups, I've changed the configuration to the opposite stereochemistry. All right, so now I'm going to prioritize them. We already did that on the previous page. Hydroxyl first, ethyl second, methyl third. That is clockwise. Therefore R, but I switched 2 groups. Therefore it's S. So S is the answer. So that's another method to do that. And of course, I urge you to do that if the hydrogen's in the plane. Super easy to make a mistake. And that's what I say in the next one, example 3, assign RS configuration to the following molecule. Never try to assign configuration when a hydrogen or lowest priority substituent is in the plane of the paper, unless you are one of these super spatial people that can, some people can just rotate these, maybe about 5% of the class can do that. They can, oh, I just walk around this side of the molecule, I can view it from here, I can view it from here, I can rotate it. If you're like that, then you don't need to go through this extra effort. But if we want to assign configuration, this hydrogen is going to be the lowest priority substituent. So we have to rank these, and then we have to imagine ourselves kind of walking over on this side of the molecule with the hydrogen away from us and visualizing these groups. And it's hard to do. And maybe you could do it while you're at home sitting and drinking a cup of coffee and doing sapling, but during the test you're not going to be able to do it. So that's why I'm trying to give you more than one technique to do this. Okay, so what I'm going to do is I'm going to exchange the hydrogen and this alkyne group here. All right, so I still have this tert-butyl group. Hydrogen's now going back. Methyl's still here. Here's our carbon-carbon triple bond. So I've exchanged the 2 groups, and I made a little note to myself so that I remember to switch the configuration at the very end. So this is opposite configuration when I switch 2 groups. This one is an especially tricky one because, you know, how are you going to prioritize these groups here? I could easily prioritize the hydrogen and the methyl, but what about the tert-butyl group versus this carbon-carbon triple bond? So I'm going to draw this sort of the, what I call the exploded view of the carbon-carbon triple bond. So we have this hydrogen going back. That's certainly number 4. Methyl is number 3. And then let's draw out the tert-butyl group so I can keep track of what's going on here. So each carbon, yeah?
Those 3 lines are like defined by, right? Not a triple bond.
These are this is the triple bond, sort of what I call the exploded view of the triple bond.
I mean, the three lines you put that, you mean, that means
This-
defined by, right? That's
Yeah,
defined by that one, yeah, that.
that's equivalent to.
That's okay, that's what I mean.
Yeah.
It's not a triple bond.
Yeah, no, that's not a triple bond. That's an equivalent to sign.
This one up here is 3, 2.
This should be a 3. Sorry about that. Let's fix that. Okay. So definitely hydrogen is 4. Methyl is 3. Let's follow this one atom at a time. So we have a carbon and a carbon, so we're going to go one more atom. Carbon, carbon. We could go here, we could go here. Carbon, carbon, hydrogen, carbon, carbon, carbon. So we could go straight to the hydrogen and then we'd be the same, but we have a higher priority. We follow the highest priority pathway. So this would be carbon, carbon, hydrogen. This would be carbon, carbon, carbon. So this group will take priority. So this is number 1, and this is number 2.
So it's S.
All right, so if we trace the groups, and I leave the 4 off. The 4 throws me off, but I'll just do it there just for the sake of that. You can leave it off. That is counterclockwise. Therefore S, but we switch 2 groups. Therefore the answer is R. That would be the most difficult type of problem. All right, I'm going to give you one more. We're going to do 3 different ways of determining this one. This is another way. It's not a usual way that you see stereoisomers drawn, but if you have one bond here, and again, this would be like if you're looking at the molecule where the highest priority is going back, or just grab the molecule, and you trace the molecules around. So this is another way of drawing stereoisomers. Again, not very common, but it is a way to draw stereoisomers. So the hydrogen is going back, and that's lovely, because now we don't have to do any shenanigans with that, right? So what we can do is 1, 2, 3. Everybody agree with that? Bromine has a higher atomic number than chlorine than fluorine. So this one here is, and we're just comparing the 2 to see what the relationship is. So that is going counterclockwise, so that's S. And then I could do the same thing over here. Bromine's number 1, chlorine's number 2, fluorine's number 3. That's R. So therefore, they're enantiomers. Opposite configuration, they're a pair of enantiomers. So this is designating RRS configuration to each and compare. We could have actually made 2 models and compare. That can be time consuming. And some of you will do that, and that's fine. But I just want to give you alternatives. So if we made the 2 models and then compared them, we would be able to see that when we tried to line up the bonds, two of the atoms wouldn't be able to line up. Okay? So number 1 would be that. Number 2 is what we just did. So opposite configurations. Therefore, enantiomers. Now, if one of them was drawn with the hydrogen in the plane or something, it would be a little more hard work to assign the configuration. So I'm going to give you a third way of doing that. And that's to see if any 2 groups have been exchanged. All right, so this is going to be the fastest way and the least prone to mistakes. Notice the hydrogen's back, the bromine's coming forward, it's on the left. And the only difference between this one and that one is that 2 groups have been switched. Right? That's the only difference. So if you exchange these, you get this. That is one exchange, therefore they're the opposite configuration. It matches number 2 after one exchange. Therefore, they must be enantiomers. That is the fastest way of all. And it's the way that's going to give you the least likely chance of, if you do number 1, less likely to finish the exam. Number 2, easy to make a mistake when assigning S and R. So easy to make a mistake. All right, questions on assigning configuration? Yeah?
What did you mean by it matches number 2?
If I exchange these two groups, I get the second one. We'll call it, maybe I'll make it more clear if I call this number 1
Oh.
and number 2. Yeah. All right, so yeah. If it's a little harder to keep track of 2 exchanges, but if there were 2 exchanges, then that would mean they're the same compound. Because one exchange switches to the enantiomer. If there's 2 exchanges, then you're right back to the original configuration. All right? All right, let's talk about molecules with more than one stereocenter. Many organic compounds have more than one chirality center. The more chirality centers than a molecule has, the more stereoisomers are possible. So let's look at 2-bromo-3-chlorobutane, and I have 2 asterisks here because I have 2 stereocenters. All right, so on the next page, there are 2 stereocenters. How many stereoisomers can we draw? Well, let's see. We have 2 stereocenters, each of which could be R or S. So this is really a statistics question, isn't it? Which could be R or S. So here's our possibilities. We could have both be R, RR. We could have both be SS. We could have one be S and one be R. The one on the left S, the one on the right R. Or we could have the one on the left R and the one on the right S. So that's 4 altogether. So 4 possibilities. And it turns out that, so for the maximum number, sometimes we're not going to have this many. In this case, we have 4. But the maximum number of stereoisomers is 2 to the n. In this case, since we have 2 stereocenters, it would be 2 squared or 4. And as we're going to see coming up, we don't always have 4, but that would be the maximum number. So if we have 3 stereocenters, there's 8 possibilities, 2 to the 3rd. All right. Now, I have drawn out all 4 of these stereocenters here, and I've drawn them out in the same order that I have here. So the first one is RR. And we're going to be doing some of these in discussion next week. And really, if you're going to assign configurations to all 4 of these, you really only need to do it for the very first one. So for the first one, we would have number 1 would be bromine, number 2 would be this group here, and number 3 would be methyl. So 1, 2, 3, so that's R. And then I love it when the hydrogen's already drawn going back, don't you? Over here, this would be number 1, this would be number 2, and this would be number 3. That's also R. And now I can Just doing that, I can now assign configuration to all the rest. So notice here on the left-hand side, I have switched the bromine and the hydrogen, haven't I? So that means that one's S. I've also, let's look on the right-hand side, what have I done? I've switched the chlorine and the hydrogen, so that's also S. So remember, when we do a switch like that, we change to the opposite. All right, now what about number 3? Let's see. The bromine and the hydrogen and the methyl match this one. So that's S. What about the right-hand side? What does that match? R. That's R. What about left-hand side on number 4?
R.
That's R. And what about the right-hand side?
S.
Everybody seeing this? Okay. So this matches exactly what we're talking about here. We're going to stop right there and we will continue this next time.